In this video, we have two short examples, and in the first one, I'm taking a curve in rectangular form and converting it into its polar form. In the second example, I'm taking a curve in polar form and converting it into rectangular form. So if I look at my first example, that's a very recognizable equation. That's a circle of radius 3 centered at the origin, and it's exactly the same thing I see in the plot down below. So you may guess immediately what the polar form of this equation is, but I want to illustrate the formal conversion. And so we replace x with r cosine theta and y with r sine theta. When we sub these into the equation, now I can factor an r squared out of that. And then I notice I have a cosine squared plus sine squared, and there's an identity for that. That's 1. And I end up with r squared equals 9. Now the interesting thing about this result is I get two valid polar equations that give me the same graph. The first equation says no matter what the angle is, I'm going to go to a distance of 3 from the origin. So if I aim at theta equals 0, I go a distance of 3, I get this point right here. If I aim at theta equals pi over 2, I go straight up by 3 units, and it traces out a circle. But r equals negative 3 is just as good. If I aim at theta equals 0, I just go backwards 3 spaces, and I land at this point. If I aim at theta equals pi over 2, I go backwards 3 spaces, and I land at this point, and so on and so on. So the second equation is really tracing the same circle. It's just the sequence of the points being plotted is slightly different. In our second example, we start with this polar equation, r equals secant theta tangent theta. And one of the standard tricks for converting to rectangular coordinates is when you see an r, try to make it into an r squared. So I can multiply both sides by r. And that's a good thing because we're planning to use the relationship r squared equals x squared plus y squared. But now I need to get into the right-hand side, and to convert to x's and y's, I want to express that in terms of cosine and sine. So the tangent is sine over cosine. The secant's 1 over cosine. That gives me 2 factors of cosine in the denominator. And I'm happy with the numerator there because that can be replaced with y. In the denominator, though, I have those lonely cosines, and I need to stick an r to each of those in order to find x out of this expression. Well, conveniently enough, I can just divide both sides by r squared, and I recognize on the right-hand side that I have a y in the numerator and an x squared in the denominator because x is equal to r cosine theta. Solving for y, I get a very familiar curve out of this, and I also recognize it in the picture. This is the simplest parabola, y equals x squared, passing through the origin. Okay, that's it. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.